So recall the seed object, mathcal I, gamma, and pi. And this is a three-tuple, which contains the full geometric object, so the seed object, or we can think of the interface construction, mathcal I, to be the full geometric object with its one skeleton, its subset, subgraph, the piecewise isometry group, which is sort of like in CW complex language, or algebraic topology language, it would be a piecewise cellular map. It's just kind of reshuffling cells around in certain geometric ways. Like you can't just just shuffle them in any which way. They have to kind of go in certain geometric ways. So some sort of parity condition is involved. So the three-tuple, it's a three-tuple. We encode our basic object. It's essentially a geometric object with a symmetry group and a graph on the intersection loci. So we can express gamma in the following way, as the union of pairwise intersections and unioned with the quadruple point intersections, and there will be 6 of these based on previous construction of the object here. We're assuming, like, if you want to read, if you haven't seen it and you want to read more about it, it's in my channel description. It's my blog, JZ Dynamics. We basically, that's how you define it. These are edges, so we're unioning the edges to get like some sort of connected graph. And really, it can be interpreted more than just a discrete, more in the sense of graph theory, classical graph theory. It can be interpreted as a smooth graph, and even a quantum graph. So we can sort of localize the flows or the waves, differential objects on the 2 cells, kind of restrict them to the locus here, the graph locus. So we can get a quantum graph, and this would be an equal length quantum graph, because all edges are, due to symmetry, basically all edges are going to be the same, which is nice, sort of like combinatorial graph. So yeah, piecewise isometry group it acts on the geometric structure and it does some interesting things, especially at the gamma set. So we just basically, all in all, we have a geometric object, a subgraph, and a symmetry group. So this brings me to this page 2, which would be, if we color the edges of gamma, we can appreciate the group structure a little bit more easily. For example, a simple choice of colors, we can get a nice group description, isomorphic to a known group. And this group turns out to be the G sub 2 by 2, the pocket cube Rubik's Cube group. This is the Rubik's Cube group, and this is under, I'm assuming, the quarter turn metric, at least, going forward. So essentially, gamma has 6 vertices, the quadruple points. It has 12 edges and is 4 regular. The gamma decomposes into, it decomposes into three planar subgraphs. So these are, when you slice the CW complex, or the mathcal I, the interface construction, you slice it along coordinate planes. If it's centered at 0, 0, 0, and In 3 space, then you'd get, x equals 0, y equals 0, z equals 0 planes, slicing it, and you would get a two regular graph on each of those planes, those coordinate planes. So define a coloring or a labeling equivalently of the edge set of gamma. We define this map from the edge set of gamma to these labels or colors, purple, orange, blue. In particular, we'll map a distinct color to each two regular planar graph. So that's the coloring scheme going forward. Assume that Math.Ca is a subset of, like I said before, subset of centered at 0, 0, 0 in 3 space. And gamma is a subset of Math.Ca, which is a subset of this cube in 3 space. For reasons of symmetry, like I said before, we're gonna each planar graph lies on a coordinate plane, and the union of all those 3 planar graphs gives us the full gamma graph, and we can express that as follows. This nice decomposition into the first the planar graph on the first x coordinate, or first coordinate, the planar graph on the second coordinate, planar graph on the third coordinate.